This is a recording of a presentation given at Highways UK in 2021 by Andy Stevenson, and I am the Associate Director of Road Services with W.D.M Limited. Pavement management is a key component of any highway asset management system. And for an asset management system for highways to be truly effective and to achieve the maximum possible beneficial outcome over time, in terms of pavement life, financial efficiency, and the delivery of a consistent level of service to the highway user, requires a considered, reasoned approach, which is based on objectivity rather than subjectivity. Now, this has long been recognised in national publications. The ones on the screen date back over the last 10 years. In 2012, we had the Potholes Review, Prevention and a Better Cure. The key word there is prevention. And in 2013, we had the Highways Infrastructure Asset Management Guidance, which advocated a joined-up approach and a reasoned approach and a strategic approach to the management of the highway asset. And then finally, in 2016, we had well-managed highway infrastructure, which was itself an update to the previous code of practice, which was entitled well-maintained highways. All of these documents advocate the adoption of a reasoned, risk-based, objective management philosophy for what is, after all, the most valuable public asset, both in terms of financial and also as a means of facilitating mobility and service delivery across our nation. For many rural parts of the UK, the highway is the only means of connectivity between communities. It's not just the car, it's buses, bikes, delivery vehicles, all need the highways. There is no viable alternative. But the meeting at and the conference at Highways UK last week also has to be set against the backdrop of COP26, which was meeting simultaneously in Glasgow. And from the UK's perspective, a commitment to reach net zero CO2 emissions by 2050. In achieving this target, it is inconceivable that the UK's most numerous and valuable public asset will not need to play a significant part in achieving those sorts of carbon reductions. And yet, if you were to ask the general public what was the most significant issue on their local highway network, I'm sure that one word would prevail. You would hear it time and time again, and that word is potholes. We tend to focus on what we can see, even if we can't objectively measure it. It becomes how we judge things. And so the slide that you're looking at now shows typical defects as manifested on the UK highway network. The top row shows 3 defects, which are typical of the failure mechanisms of modern surface courses. On the second row, the bottom left shows a typical surface dressing failure or deterioration. And then on the bottom right, we see a surface that is deteriorating. Hasn't started to fail yet, but it is well on the way to complete failure. And within a short period of time, it will look exactly like those pictures on the top row of the slide. So, Why do we measure, or why do we appear to measure at the moment, our highways on the basis of failure? For that is what potholes are. After all, when we go to the dentist, we don't ask him or her before we sit down in the chair how many fillings they gave last week and use that as our benchmark. So why would we do that with our highway network? For many years, the UK has had a system of measuring its road condition, utilising survey vehicles that comply with the UK Roads Board scanner specification. These vehicles measure over 40 different parameters, and yet we have generally focused on the 5 or 6 that contribute to the Road Condition Index, generally known as RCI. This index is used to benchmark local highway authorities against each other so that the DFT can get an understanding of the overall condition and trends of the local highway network. It doesn't represent what we see happening in front of us, is the challenge that is often thrown at this RCI. And no, it doesn't, because the RCI was never meant to do that. It was, and is, a network comparative technique, which allows the comparison of one network to another in an objective way. The real wealth of this survey technique lies in the rest of the data that does not feature in the RCI. Now, these surveys have sometimes been referred to as legacy surveys. And in a way, that's correct, but only insofar as the dictionary definition of legacy, which is something from the past that benefits the future. We have, over the last 15 years, as a highway industry, built up a huge archive of condition data, which, if analysed correctly, will enable us to predict objectively the future performance of our highway networks. Analysis of the raw data collected by W.D.M's road assessment vehicles, or RAVs, which comply with the scanner specification, using a grid of 100 by 100 millimeters longitudinally and transversely, enables an accurate measurement and therefore an accurate prediction of the variability of the highway surface. This is a good measure of deterioration, and it can be tracked over time from one survey to the next. And if we can measure deterioration, then we can also accurately predict deterioration in the future, and in doing so, define an appropriate intervention time. These data sets are available on any W.D.M road assessment vehicle survey, and we have data sets for the last 2 years for any survey that has been undertaken by W.D.M. The next few slides show the defects that we saw earlier and give us a measure of surface variability. This slide here gives us a view of how we might represent the data coming off this 100 by 100 millimeter grid. So what we're looking at here in the top left quadrant is a strip map which shows the data, 1 meter data. So it takes an average of the 1 meter, all the data squares in 1 meter, and represent them on this chart. We'll see three lines, one of which is the near side wheel track, one of which is the whole carriageway wheel track, and the other of which is the offside wheel track. And then in the bottom left quadrant, we actually see those numbers set out for us. Now, the colours that we see before us are based on a series of thresholds that have been implemented and put into the software, and we know where the trigger points are, where we get transitions between different phases of a material. Each material that we see on the road, to some extent, has its own, for want of a better expression, fingerprint, its own variability characteristics. And we can use that to determine when a material is static or beginning to show signs of deterioration. In terms of the colours, green does not necessarily mean good, it just means low variability. White is an average variability, amber is above average, red is at the top end of the distribution, and when it's really, really high, the colour is manifested on the strip map and on the bar chart at the bottom left as grey. So let's look at some of those defects that we looked at earlier. So what we see here is a bend with some high friction surfacing on it. And we see on the right a strip map which shows us the near side, offside and whole carriageway distribution, and also the bar chart which shows you the individual readings. And you can see there's a significant difference between the near side and the offside. But if we compare 1 year to the next, and these surveys were taken, as the slide shows, in 2020 and 2021, they are the same place, the same road, and the same location on that road, on that bend, as the map shows. So what we can see here is that there is a clear difference in terms of the deterioration or the variability as measured using the technique that we are talking about between 2020 and 2021. And bear in mind that the data that is used to derive this comes from a machine that has been accredited by TRL in some very detailed tests and undergoes a rigorous QA regime. So we know the data is accurate. And we can clearly see that certainly in the near side wheel track, between 2020 and 2021, the level of variability and therefore the level of deterioration has increased significantly. Looking at another of the defects, we can clearly see that in 2020 some flux material, some reactive maintenance had taken place to fill what was clearly a very highly area level of fretting. And in 2021 we can still see that patch repair. But if we look at the black marker bar on the strip map in the middle picture of each side of this screen, we see a black line, and that black line is where the machine actually is. And if we look at the bar chart at the bottom on both the 2020 and 2021 data, we can see that that level of variability has significantly increased over that year. Similar picture here, slightly different road, but nevertheless a similar sort of surface. This is actually the slide that was in the bottom right hand. The picture in the top left of this slide is the picture was in the bottom right of the first slide that we saw. a road in 2020 that was near failure. In 2021, we can see it has started to fail significantly, as you can see by the area of fretting in the foreground of the forward-facing video. And that level of fretting is manifested and measured in the strip maps and also in the bar charts. Clearly, we can see by looking at the bar charts at the bottom that the level of deterioration has increased significantly, and the large bank of grey that we see on the near side wheel track, the right hand 2021 picture, is indicative of the fretting failures that we see in the forward facing video. Now, as I said earlier in the presentation, green does not necessarily mean good. It just means low in terms of surface variability. And some materials, most notably surface dressing, quite often fails due to a reduction in the surface variability. What we are seeing here is a surface dress road where the chippings have effectively become embedded in the layer of bitumen that is used to help the chippings adhere to the road in their early life. Most surface dressings perform over time by achieving this embedment. But if we get over embedment, the bitumen rises to the surface and can leave a rather sticky, shiny and slippery surface. Now in the UK, this is quite often known as fatting. In New Zealand and elsewhere around the planet, it is known as flushing, which is perhaps a better expression in terms of the binder flushes to the surface, but the process is the same. And what we can see here is a road that has been surface dressed and has achieved over embedment. Now, this may be because there was too much binder put down in the first place. It may be that there's been a very hot summer and been a lot of heavy traffic that has warmed the surface of the road up and allowed the traffic to drive the chipping into the bitumen and the road surface. Sometimes you see it if you've got multiple layers of surface dressing, and it can quite quickly become a bit of a mess. But nevertheless, the point of showing this slide is to show that the technique works at either end of the spectrum. And so if we know where the optimum threshold for a particular material lies, then we can begin to track back to and use historic data and subsequent data to understand how the surface variability is moving over time. And in understanding how a particular material behaves in a particular set of circumstances, then we can reasonably predict and accurately predict where we might want to intervene. So the whole point of what I have just shown you is to demonstrate that the data, the objective data needed to manage our road networks in a proactive way already exist. And it is only by being proactive that we will be able to assist in driving down the carbon footprint of our highways. So as this slide says, historic data allows us comparison between years, which will enable a number of things. The objective identification of changes in the road surface from previous data sets. It will allow us to identify the trigger points that I have talked about, particularly for preventative treatments. The identification of locations where soft touch treatments at the optimum point in the material's life cycle will significantly extend the life of the asset. All of this will in turn reduce the formation of potholes. If we intervene early at the right time, we will stop potholes forming, and that has to be the best way of dealing with that particular blight. It will also reduce the consumption of mineral aggregates and oil-derived binders, and that has to be a significant issue for us as we look forward over the next 30 years to chasing down the net zero target. But more than that, if we are able to put a material in place and keep it in place for a significant period of time, we will also reduce the amount of CO2 that's associated with highway maintenance activities. The current approach of reacting to potholes is hugely inefficient, but it's also hugely costly in CO2 terms. Just think of all of the trucks that have to come and remove material from the road surface, all of the machinery that's needed to dig out aggregates, to mix new asphalt, to bring asphalt to a site, to lay it, and to compact it, all using fossil fuels. Anything that can reduce that amount of activity gains us wins in terms of reduction of CO2. But it is also financially efficient. It is generally reckoned that reactive maintenance costs 5 times as much as proactive, planned, preventative maintenance. So the techniques that we have discussed in this presentation will ensure that highway managers are able to maximize their financial efficiency and significantly contribute to their corporate decarbonisation agendas. So thank you for your attention and sticking with me to the end of this presentation. If you would wish to discuss any of these things, I can be contacted on the details on the screen. So I conclude by thanking you for your attention.